For the shown stress state, sketch proportionally more circle and subsequently find the principal normal stresses as well as the maximum shear stress. Represent the stress state element for both cases are principal stresses and maximum shear stress. Superposed on the original shown element, find the stresses on plane AB using the transformation equations and plot the corresponding stresses on Mohr circle. Angles on stress state elements and Mohr circle must be clearly indicated. So here is the original picture or diagram for the Mohr circle. So first thing first, you need to classify what is normal stress in the x direction, y direction, and the shear stress. So here what I did for it, so normal stress in the x direction is -5 megapascal. Why? Because it's being pressed, right? Normal stress in the y direction is 8 megapascal because it's being pulled out, and the shear stress is 2 megapascal. All right. So the strategy is first find the center of the circle. So that center or the average stress is equal to the normal stress in the x direction plus normal stress in the y direction divided by 2. Then I have -5 plus 8 divided by 2, which is 1.5 megapascal, and the center is at 1.5, 0. The radius of the circle is equal to this equation. Okay, so plug into the value for it. I got 6.8 megapascal for the radius. And then here's my Mohr circle. Let me pull this up a little bit so that you can see it. So here's my Mohr circle. So the circle in the center is right here. So this is my x-axis as normal stress, y-axis as shear stress. And since the center is positive 1.5 megapascal, 0, so it's going to shift to the right. Okay. So I have the distance from the original coordinates to the center of the circle is 1.5, right? And the radius is 6.8. So this is not in scale. All right. Now, for the first case, you ask to represent the Mohr circle or the transformation of this diagram for the case of principal normal stresses. So what is the normal stresses for this one? The principal normal stresses. So the principal normal stresses for this Mohr circle is happen to be at the intersection of the circle with the x-axis. So right here and right here. So you have two x-axis, 2 points for to intersect. Okay. So normal stress 1 is equal to the distance from the original coordinate to the center plus the radius. Okay, so I have 1.5 plus 6.8, which is 8.3. So that is the coordinate of this point, and the coordinate of this point is equal to this distance subtract the radius, which is -5.3. Right, so I got normal stresses, the principal normal stresses on the Mohr circle. All right, now for to find the angle. So here's the representation of it. So you have this line AB. Oh, where's my B? Let me put it in. All right. So my reference point is A -5.2. Right. You can, yeah. All right. Now for the angle of this one, so you can use either this angle from line AB to normal stress. So either this angle or this angle is the same. Okay, so I'm going to use yes, the same. Since it's the same, so I'm going to use this angle because this triangle is oriented in, I would say, quadrant 2. Okay, now what is the how do we find the angle of this one? So since you have when this object, this short, is going to create two angles at the two axes. So you have, that's why you have two theta. One theta is in this angle, in another theta is in this angle. So I combine them to get two theta. Okay. So I have a tangent to theta equals shear over the normal stress in x direction minus normal stress in y direction divided by 2, the average of that, not the average, but yeah, just take what I wrote here. All right, so plug in the numbers and then I figured out theta equals 8.55 degrees. Right, so here's my distortion. So originally you have it like this, right? So you have square, the bottom leg is perpendicular to, is parallel to the x-axis. It's parallel to the x-axis. Then because of the distortion, so the this square rotate counterclockwise. Remember, counterclockwise at the angle of 8.55 degrees. So since is the square rotated counterclockwise, this angle at this axis is also rotate counterclockwise at the angle of 8.55 in this axis. So that's why I have two theta. Remember what I said earlier? So you count this angle and this angle. That's why you have two theta. All right. So here it is for the first case of principal normal stresses. Now for the case of maximum shear stress. So the maximum shear stress happens at, back to this one, the Mohr circle. So you found the radius of the Mohr circle, right? So the maximum shear stress happens at the surface, or yeah, at the surface of the Mohr circle, typically up, down, or left, right direction, because it's a right angle. So we easily find those unknown information if we asked. But my point is the maximum force, the maximum shear force is anywhere on the surface, on the circle. Okay, so that's why I have a maximum shear stress equal either positive or negative radius, which is 6.8 megapascal. All right. Now, what is the angle for the maximum shear stress? Well, in this case, you found that the, back to this one is easier to represent. Now let me go down here. Okay, so on the lower left corner on your video. So in the first case, when you have a principal normal stresses, you found out this angle is being to be 5 point, never mind, 8 point, is 17.1 up here. So you found out this angle is 2 theta, which is 17.1. And now for the maximum shear stress, it's going to go clockwise, opposite direction of the principal normal stresses. So this angle is going to be equal to 90 degrees minus this angle. Okay, so again you have 2 theta, because this angle is the same as this angle, and you have theta, so 2 theta. 90 degrees minus 2 theta, I call this as a theta prime. Okay, to differentiate with this one. So I have 90 degrees minus 17.1, I got 72.9. Now theta prime is equal to 36.45. So over here I have xy coordinates, and this should be x prime, y prime, if you would say. Okay, so here's my xy axis and x prime, y prime. So like I mentioned earlier, so for the maximum shear stress, it's going to go clockwise, so rotate like this, and initially it's at x, and then it rotates 36, rotate clockwise 36.45 degrees. Then it ends up being in this shape. Okay, this form, and the maximum shear is 6.8 megapascal. Okay, and for the other stuff, you can do whatever the question asks you to do, but this is the basic concept and the process. So I hope that makes sense. That's it.
If you find the video is helpful, feel free to give it a like, share, and subscribe to my channel in order to receive the most current videos. Don't forget to hit the bell so that you won't miss anything. I'll see you next time.